Rainbows. You've seen them countless times, haven't you? They've graced the sky after a rainstorm, brilliant arcs of color, vibrant and mesmerizing. You probably think you know what they are. Light passing through water, splitting into colors. Simple, right? You've learned this idea in school, and it makes sense. Light bends when it hits water, and suddenly, you see colors. But hold on. This is where most people stop thinking. The truth? You don't really understand what's happening. You just accept the label and move on. And that's the problem. So, let's take a moment and dig deeper. What's actually going on when a rainbow forms? You can't just say refraction, because that's another label. Why does light refract when it passes through water? Why do the colors always appear in that exact order? Why does red sit at the top and violet at the bottom? And here's a good one to ponder. Why can't you ever reach a rainbow? You can chase it for miles, but it stays the same distance away. It moves, but it never gets closer. Why is that? Most people would just shrug and say, that's just how rainbows work, and leave it at that. But this is where we make a critical mistake. We stop asking questions. We forget that what we're witnessing is a physics demonstration unfolding right before our eyes, an intricate dance of light, water, and geometry, and yet we're content to call it just a rainbow and move on. In truth, the rainbow is a far more sophisticated phenomenon than you've ever realized. It's a window into the fundamental mechanics of light, revealing secrets about electromagnetic radiation, how light interacts with matter, and why the universe has color in the first place. And all this you thought was just pretty. But there's so much more going on, and once you understand it, you'll never look at a rainbow, or light itself, in the same way again. Let's break it down. First, let's start with what you think you know: light. You see light every day. It's what lets you see the world around you. But light isn't just light. It's electromagnetic radiation. This is the same fundamental force that holds every atom in your body together, the same force you feel when two magnets push apart. It's invisible, but it's everywhere. Light is the oscillation of electric and magnetic fields, traveling through space at an unimaginable speed, 792,458 meters per second, to be exact. And this electromagnetic force is the very same force that is responsible for the rainbow you see in the sky. But here's where things get interesting. The light that forms the rainbow isn't just pure light. It's not just white. White light is actually a chaotic mixture, a blend of every visible frequency all squashed together. Red, orange, yellow, green, blue, indigo, violet, all of these colors exist inside white light, but you can't see them unless you separate them. A rainbow doesn't create these colors. It reveals them. White light carries all the colors, but the rainbow sorts them out. It untangles the mess of frequencies and lays them out in a perfect sequence, from red to violet. What Newton figured out 350 years ago with a prism, a raindrop does in the sky. It separates the different frequencies hidden inside white light and exposes them to your eyes. Now, let's focus on a single raindrop. Imagine it hanging in the air, tiny, spherical, about 2 millimeters across. Light, which is a mixture of all those frequencies, enters the raindrop. But here's the thing you may not know. Light slows down when it enters water. In a vacuum, light travels at its maximum speed. But in water, it slows to about 75% of that speed. It's not a big difference, but it's enough to change everything. What happens when light slows down in one part of its wave while the other parts are still moving at full speed? The light bends. This bending is called refraction, but that's just a label. Refraction happens because of geometry, and it's inevitable. The light that enters the raindrop bends toward the slower medium, the water, because one part of the light wave hits the water first and slows down before the rest of it does. Think of it like a shopping cart with one wheel in the sand and the other on concrete. The cart turns. The same thing happens to light, except the bending is on a much smaller scale. So the light bends as it enters the raindrop. But that's not the end of the story. The drop is spherical, and when light hits the back of the droplet, some of it gets reflected, bouncing back toward the front of the droplet. The light doesn't just pass straight through. The back of the raindrop acts like a mirror. This is where the rainbow starts to take shape. We'll pause here. I know this is a lot to absorb, but we're just getting started. Are you ready to dive deeper into the physics of the rainbow? Because things are about to get even stranger, and understanding them will change how you see not just rainbows, but everything that happens in the world of light. Now let's continue. So we have light bending as it enters the raindrop, and then something critical happens. After bending, the light hits the back surface of the droplet and reflects. This is where things start to get more interesting. When light enters a raindrop, it behaves almost like a tiny, perfect prism. The spherical shape of the drop means that light doesn't just bend once. It's reflected off the back and then refracts again as it exits the raindrop. This is a crucial part of the process. You see, when light exits the raindrop, it doesn't simply pass back out in the same direction it came in. It bends again. And this double refraction, first when the light enters and then again when it exits, spreads the colors apart more and more. It's like stretching out a slinky. The wavelengths of light, each color's different frequency, are pulled apart, separated, sorted, and each one exits the raindrop at a different angle. But here's the part that makes everything really click. Not all light bends the same amount. Red light, for example, bends less than blue or violet light. Every color of light has its own refractive index when it enters the raindrop, meaning that each color is slowed by a different amount. This is why you see the colors of the rainbow in that specific order, why red sits on top and violet is at the bottom. Each color has a different path to follow, and that's exactly what causes the separation. For those of you who might be thinking, so what? It's just light bending. Let's break it down a little further. The red light bends the least because its wavelength is the longest. Violet, with its shorter wavelength, bends more. The process that happens inside each raindrop ensures that the different colors, red, orange, yellow, green, blue, indigo, and violet, are separated and fanned out in the correct order. This phenomenon happens continuously across millions of raindrops in the sky, and together they form the rainbow we see. The colors are separated because of a precise mathematical relationship. The bending of light, the angles at which each color exits the drop, is determined by the physics of refraction and reflection, and the specific refractive index of water. This is a perfect example of how the geometry of space, the properties of water, and the behavior of light come together in harmony to create something as beautiful as a rainbow. Now here's where things get tricky. You might be wondering, if each raindrop is doing this, light entering, bending, reflecting, and bending again, then why don't we see a rainbow from every drop? Well, that's because of something important. You only see the light from a particular set of raindrops at any given moment. Each raindrop sends its light out in a specific direction. The angle of the light exiting from each raindrop is fixed. For you to see a color, the drop has to be positioned at just the right angle relative to you and the sunlight. Think about it like this. For every color in the rainbow, there's a precise angle that the light needs to hit your eye. Red light exits the raindrop at about 42 degrees, while violet light exits at around 40 degrees. This small difference in angle is what creates the rainbow. But the catch is, the light you're seeing comes from specific drops at those exact angles. As you stand and look at the rainbow, you're seeing light from millions of raindrops, each positioned at these very precise angles, each sending light in a specific direction. If you move or change position, the entire rainbow shifts because the angles change. This is why you can never really reach a rainbow. It's not a physical object you can walk toward. The rainbow exists because of the geometry between you, the sun, and the raindrops. If you walk toward it, your perspective changes, and new raindrops enter the critical angles. The rainbow doesn't move. It stays in the same relationship to your position, and it remains exactly as distant as it always was. It's an optical phenomenon that exists only in relation to where you stand. It's not something that can be touched or physically approached. It's this geometry that makes the rainbow a personal, unique experience for each observer. The rainbow you see is not the same rainbow someone else sees, even if they're standing right next to you. The light that reaches your eyes is from a specific set of drops positioned just right to give you that exact rainbow. The person beside you has a slightly different angle and sees a different set of drops, and therefore a different rainbow. It's an individual experience, dictated by your position and the geometry of light interacting with the raindrops. This is what makes rainbows so mystifying and beautiful at the same time. The science behind it isn't just about light and color. It's about understanding geometry, optics, and the way our eyes interact with the world around us. You can't just see a rainbow. You can only experience it from your own unique position in space and time. But wait, there's more to the story. You might also have noticed that sometimes there's more than one rainbow. One is bright and the other is fainter. These are called secondary rainbows, and they occur because the light reflects twice inside the raindrop before exiting. This extra bounce changes the angle at which the light leaves the drop, making the second rainbow appear with its colors reversed, violet on top, red on the bottom. The secondary rainbow is always fainter because it loses some intensity with each reflection. But it's the same physics, the same process, just with one more bounce. And sometimes, under the right conditions, you can even see supernumerary arcs, which are additional faint bands of color inside the primary rainbow. These extra bands don't happen because of simple refraction. They're interference patterns. These patterns happen when light waves interact with each other, reinforcing or canceling each other out. This is the proof that light behaves as a wave, not just a particle. And it's these very patterns that give rise to the subtle beauty of the rainbow, showing us the wave-like nature of light in action. The rainbow is more than just a colorful arc in the sky. It's a window into the fundamental nature of reality itself. It's light, geometry, optics, quantum mechanics, and the structure of the universe coming together in a beautiful, vivid demonstration of how nature works at every scale. Understanding this gives you a glimpse into the true magnificence of the universe, and it all starts with the rainbow. Now let's take things a step further. When you look at the rainbow, you're seeing all these colors split apart into their individual components, but it's not just random. There's a mathematical and physical reason behind why the colors separate and why they appear in the order they do. It's all about the light's wavelength and the properties of water. The light that enters the raindrop is made up of many different wavelengths, with red light having the longest wavelength and violet the shortest. As each wavelength bends when it enters the water, they don't bend the same amount because of how each wavelength interacts with the water molecules differently. The bending, or refraction, happens because light is slowing down as it moves from the air into the denser medium of water. But the amount of bending is different for each wavelength. The longer wavelengths like red light bend less than the shorter wavelengths like violet light, which bends the most. This difference in bending angles causes the colors to fan out and spread apart. The angle at which the light exits the raindrop determines where each color will appear in the sky. Now, let's talk about the second part of the process, reflection. After the light enters the raindrop and bends, it hits the back surface and reflects. This reflection is key to the rainbow's formation. Without it, the light would just pass through the raindrop and continue in a straight line, and you wouldn't see the rainbow at all. The light bounces off the back of the raindrop and heads toward the front surface. When it reaches the front surface of the raindrop, it refracts once again before finally exiting the raindrop and heading toward your eyes. This is a crucial part of why rainbows look the way they do. The two refractions and one reflection combine to create the spread of colors. But as light passes through the drop and undergoes these multiple interactions, it's not just bending randomly. There is an exact, precise relationship between the angles at which the light enters, reflects, and exits the raindrop. The light is bent according to very specific laws of geometry and physics, which is why the rainbow appears as a smooth arc across the sky, with red on top and violet at the bottom. When you look at a rainbow, you're seeing the product of millions and millions of tiny raindrops, each of them behaving exactly the same way. Each one refracts the light, reflects it, and then refracts it again. And yet, the light that leaves each drop travels in a specific direction, creating the beautiful and perfect arc that we recognize as a rainbow. The shape and size of the rainbow depend on the angle at which the light enters the raindrop, and this angle is always consistent. But here's where it gets even more interesting. As you look at the rainbow, you're only seeing light from specific drops at specific angles. The rainbow doesn't exist in one fixed location in the sky. It's not a physical object that you can reach. The rainbow is simply the result of the way light interacts with the raindrops, and your position relative to those drops defines what you see. If you change your position, the entire rainbow shifts. The drops that were contributing to the colors of the rainbow are no longer in the critical angles, and new drops take their place. That's why you can never reach a rainbow. It's an optical illusion that exists only in relation to your position. And even more fascinating, the rainbow you see is not the same as the rainbow someone else sees, even if they're standing next to you. This is because of the geometry of the situation. The rainbow you're looking at comes from a specific set of drops positioned just right to give you that particular view. The person standing next to you is seeing a slightly different set of drops, and therefore they see a different rainbow. In fact, the rainbow you see is yours alone, a personal experience dictated by your position, the sun's position, and the angles at which light interacts with the raindrops in front of you. This is what makes rainbows so magical and mysterious. They exist only in the space between you, the sun, and the raindrops. And that's not just poetic. It's physics. The rainbow is a direct consequence of the light's properties, the way it interacts with matter, and the way our eyes perceive those interactions. It's a personal, unique phenomenon that can never be the same for two people at the same time. But what if I told you there's more to the rainbow than just the simple splitting of light into colors? Sometimes, under the right conditions, you can see not one but two rainbows in the sky. The second one is always fainter and appears above the primary rainbow, with its colors reversed, violet on top and red on the bottom. This happens because light doesn't just reflect once inside the raindrop, it reflects twice. The second reflection changes the geometry of the light as it exits the raindrop, which is why the colors are reversed and why the secondary rainbow is always fainter. The extra reflection causes some light to be lost, so the intensity of the secondary rainbow is weaker. And if you look carefully, you might even see supernumerary arcs, faint bands of color inside the main rainbow. These arcs are a product of light's wave-like nature. When light passes through the raindrop, it behaves like a wave, and when the light waves overlap, they can interfere with each other. This interference creates the supernumerary arcs, which are proof that light is not just a particle, but a wave. These extra arcs appear because light waves constructively and destructively interfere with each other as they pass through the raindrop, creating alternating bright and dark bands of color. So, what have we learned? The rainbow is not just a random phenomenon. It's a demonstration of the very principles that govern light's behavior. It's a real-time physics experiment happening in the sky, showing us the interactions between light and matter, the geometry of refraction, and the wave nature of light. It's a personal experience, shaped by your position in space and the way the universe is structured. And when you see a rainbow, you're witnessing an ancient dance of light, quantum mechanics, and geometry all coming together in one beautiful arc. Now step back and look at the big picture. A rainbow is a powerful reminder that the world around us is full of hidden complexities, waiting to be uncovered. Every time you see a rainbow, you're witnessing the result of light interacting with matter, of waves bending, reflecting, and interfering in ways that our everyday intuition struggles to grasp. The rainbow isn't just a colorful arc in the sky, it's a profound demonstration of physics, of geometry, and of the very nature of light itself. Each time you observe the rainbow, you're not just seeing the reflection of sunlight, but an expression of the universe's fundamental laws that govern everything from the motion of particles to the way we see the world. It's a moment when nature offers us a glimpse into the deep structure of reality, a snapshot of how light, space, and matter work together to create the beauty we see. So, the next time you catch a glimpse of a rainbow, don't just marvel at its beauty. Appreciate the science that makes it possible. It's a testament to how far we've come in understanding the world and how much more there is yet to uncover. The universe is stranger, more beautiful and more understandable than you ever imagined.